Wind turbines are among the most magnificent machines ever built. Towering hundreds of meters into the sky, their sheer size is breathtaking. These giants capture the invisible force of the wind and transform it into electricity that can power thousands of homes. In this video, we'll uncover the secrets behind these colossal machines. You'll see how wind turbines harness nature's invisible force, how their engineering makes the impossible possible, and how they're shaping the future of clean energy. Let's go. At their core, wind turbines operate on a beautifully simple principle. Unlike a fan, which uses electricity to push air, a turbine does the opposite. It uses the natural force of the wind to generate electricity. As the wind turns the massive blades, they spin a rotor inside the generator. That motion is transformed into clean, usable power. Modern utility-scale wind turbines almost always feature 3 blades. Why 3? That is because this number strikes the perfect balance between aerodynamic efficiency, structural stability, and cost. Fewer blades, like 2, rotate faster and cost less to manufacture, but they create more noise, more vibration, and place greater stress on the tower. On the other hand, adding more than 3 blades makes rotation smoother and slightly faster, but the extra weight added and expenses incurred outweigh the benefits. 3 blades provide the sweet spot. They spin at an optimal speed, minimize mechanical stress, and deliver aerodynamic efficiency without excessive cost. These blades are enormous. In 2026, they typically range from 80 to well over 120 meters long. Some latest designs from Mingyang and others exceed 140 meters. That's longer than a football pitch. The blades are typically constructed from composite materials, primarily fiberglass or carbon fiber reinforced epoxy, making them lightweight yet incredibly strong to withstand the enormous fatigue from millions of rotations and extreme weather. Each blade is carefully shaped with airfoil sections that vary along its length. Thicker near the root for strength, thinner near the tip for speed and lift. The airfoil is designed to minimize drag forces as the blades move through the wind. The wind has a longer distance to move over the top than underneath, meaning it moves faster over the top than underneath the blade, resulting in a pressure difference that generates a lift force on the blade and causes the hub to rotate. The blade slightly twists toward the tip. This is because the wing is not moving through the wind at the same speed at the different portions along its length. At the portion close to the hub, the blades move slowly, while at the tip, the blade is moving very fast because it's covering much more distance as it moves through the air. To the blade, the wind doesn't just come from the front. It comes from a combination of the actual wind and the apparent wind created by the blade's own motion. At the portion close to the hub where the blades move slowly, it experiences less apparent wind, while at the tip where it is moving very fast, it experiences more apparent wind. If the blade were untwisted, the air would become turbulent towards the tip and drag would simply skyrocket. The resulting vibration created by the drag can create enough mechanical stress to snap the blades. By twisting the blade, the tip stays perfectly aligned with that high-speed relative wind. To catch the wind, the turbine needs to face its direction. This is the job of the Yaw System, the turbine steering wheel. On the very back of the nacelle roof, you'll see 2 small instruments. One is the anemometer, to measure wind speed, and the other is the wind vane to find the direction. They are the turbine's nose. They are constantly sniffing the air. If the wind vane detects the wind has shifted even by a few degrees, it sends a signal to a computer. Once the computer knows where the wind is, it triggers the yaw drives. These are massive electric motors located at the base of the nacelle where it meets the tower. These motors engage a giant ring gear, a massive toothed circle that sits on top of the tower. These motors slowly and precisely rotate the entire 300-ton machine until it is pointed directly into the direction of the wind. This ensures the blades are always catching the maximum amount of energy. Right at the center of the spinning blades lies the hub. It's a single piece of cast steel that acts as the anchor for the entire machine. This is where the 3 massive blades are bolted on. Inside the hub are massive hydraulic rams or electric motors. Their job is to rotate the blades along their long axis. The hub is covered by an aerodynamic cap called the spinner. The cap streamlines the air so it flows smoothly over the blade roots, rather than crashing into the flat face of the hub. Behind the blades is the nacelle. Think of the nacelle as the engine room. It is the shell that holds everything together. It protects all the expensive machinery from rain, lightning, and heat. From a distance, it looks like a small box. But in reality, it is the size of a city bus, weighing over 300,000 pounds. Now let's look at what's inside. The very first part is this, the main shaft. It is a massive solid steel pole connected to the hub. When the wind pushes the blades, the shaft turns with the hub, taking the slow, heavy rotation of the hub and carrying it into the nacelle to start making power. The main shaft is powerful, but it's too slow. It only spins about 15 times a minute. To make electricity, we need something much faster. So, before connecting it to a generator, its speed is increased in a gearbox. The gearbox takes heavy rotation from the blades and ramps it up. It turns those 15 spins per minute into over 1,500 spins per minute, and that's what allows the turbine to actually start producing power. By the time the energy leaves the gearbox, the shaft is spinning 100 times faster. Because this part is spinning so fast, it's also where we keep the emergency brakes. If a storm hits, to prevent the blades from spinning uncontrollably, massive hydraulic calipers slam shut on a steel disc to lock the whole system down. The high-speed shaft connects directly to the most critical component in the entire machine, the generator. This is the most important part of the turbine because it's where the actual electricity is made. The type of generator mostly used in wind turbines is the Doubly-Fed induction generator. Inside the generator, there are 2 main parts that do all the work. The rotor, which is attached to the high-speed shaft from the gearbox, and the stator. The rotor is equipped with 3 sets of copper coils. The stator is also equipped with matching sets of coils. When the turbine blades spin, the rotor also spins inside the stator to convert mechanical motion into electrical power. The frequency of the electricity generated is determined by this formula. In a standard turbine with 4 magnetic poles, the math says that to get 60 Hz for a country like USA, the shaft must spin at exactly 1,800 revolutions per minute. But here's the catch. The wind is never constant. If wind dips and the shaft slows down to 1,500 revolutions per minute, look at what happens to the frequency. Suddenly, you aren't producing the power your country needs. The electrical grid is incredibly picky. It demands a frequency of exactly 60 Hz. If you feed it a frequency that's even slightly off, you could cause blackouts or damage equipment. This is where the Doubly-Fed system comes in. Since the wind won't stay at 1,800 revolutions per minute, we inject a separate electrical current into those coils via slip rings positioned around the rotor to create a magnetic field that spins independently of the rotor to make up the difference. The rotational speed and direction of the magnetic field are governed by the timing of the phases, which is precisely managed by a controller. In a perfect world, the rotor spins at exactly 1,800 revolutions per minute, which hits that 60 Hz target perfectly. But in reality, the wind is never constant. If the wind dips and the rotor drops to 1,700 revolutions per minute, the formula tells us we're only producing 56.67 Hz. You can see this is not up to 60 Hz needed in our homes. That's too low for the grid. What the controller does is that it produces 3.33 Hz to add up to the 56.67 Hz produced by the speed of the rotor. and when we add them up, it gives us the 60 Hz we need. If the rotor is rotating very fast, say 2000 revolutions per minute, which produces 66.67 Hz. You can see that's more than the frequency we need, which is 60 Hz. What the controller does in this case is that it rotates in the negative direction at the excess frequency to produce minus 6.67 Hz. That deducts the excess frequency and we are left with the 60 Hz we need. If the rotor is rotating at the optimal speed of 1800 revolutions per minute, which is the exact speed we need to generate 60 Hz, the controller will inject a steady direct current with no pulses at all, meaning 0 Hz. So the magnetic field only rotates with the shaft at the same speed, and we get 60 Hz on the stator. But in reality, the wind rotor never really rotates at that correct speed. So the controller is always adjusting the frequency of the rotor to ensure a 60 Hz output is maintained. Now that the power is safe and steady, it's ready for the long trip down the tower. These cables, thick as a human arm, carry the electricity down 300 feet to the ground. Finally, at the very base of the tower, we hit the final stage of the journey, the transformer. The electricity coming down from the generator is usually around 690 volts. That's enough for a factory, but it's not strong enough to travel long distances across the country. It would lose all its energy as heat. The transformer steps up that voltage, boosting it to 33,000 volts or more. This high voltage allows the electricity to zip through the underground lines, out to a substation, and finally into the power lines that lead to your house. And that is how we turn a simple breeze into tremendous power. If you enjoy this breakdown, give it a thumbs up and click on one of the links on the screen to watch more breakdowns like this. Thanks for watching, and I'll catch you in the next one.